So now we will go in with the general EM algorithm. So from the specific case of multivariate normal distribution, we go into the general EM. So in general, EM constitutes of starting first with initial configuration at time step 0. This is the starting point we are using. Now, as long as the stop criterion is not reached, we are repeating these steps. We are at the step E as assessing membership HIT. So the membership is basically the posterior probability, the probability that XT, according to current configuration here at step L, is associated to group GI. So the probability of coming from group GI. And this is estimated for all clusters, for all groups, for all samples here. So from these HIT estimation, we go at the step M. So we reevaluate then the values of the parameterization of our distributions. So with the multivariate normal lie, it's the prior mean vector covariance matrix for each group. So we need to reevaluate it here according to the Q function here, which is the expectation of log likelihood. So we are looking at the expectation of the log likelihood of the parameterization, potential parameterization we can use. And we are looking at the next parameterization that will maximize this expected likelihood starting from the current estimation. So we need to get the current estimation, and then we will make a new estimation that will be better somehow compared to what we have so far. And once we repeat this, so we evaluate. So we go with step E, step F, step E, step M, and so on. So we are reassessing memberships. We are reevaluating the parameterization, from which we are reassessing the membership, from which we are reevaluating again the parameterization until it converges or until we exhausted all the available capacity, computation capacity, for example. And in the end, we are returning the final configuration as the result. So if we look at the application of EM algorithms over two groups, we have this thing here. We see two starting points. So basically, we have this white dot here and that white dot there. These are the mean vectors. But we can see that underneath that, we have multivariate normal distribution. And so we see how the frontier and the separation between the two groups. And so at the second iteration, they are moving quite at different positions. So at first they were there, and then they will move from there to here. So the lowest one is moving to the left, and the topmost is moving even more to the top. Or no, it's moving down. Sorry, it's moving down here that way. And as such, we see several movements, and in the end we reach that result, which is kind of reasonable given the distribution of our data, even though the frontier may be closer to that. So that's one thing. You can see that the results seems to be quite reasonable in terms of clustering compared to the labels we have in our data set that is not used for learning. Likewise, for three groups, we have this kind of results. So at first, we are starting with 3 random points. We initialize in some ways. Often we are initializing from the k-means clustering. Here we see the adjustments that are made, and basically we have this kind of results. It moves from here, I would say, the one at the top going down that way, the other one is going that way, and oops, sorry. The last one is moving down. So we have these three centers that are moved, but we need to also have in mind that the covariance matrix is also changing, which is not directly seen here, except from the frontiers. We can guess somehow the shape of the covariance matrix and what it implies in terms of frontiers. So again, the results here are quite interesting. Some notes on EM. The fact is that the initialization of the algorithms is super important. And usually we are using k-means for doing it. Why k-means? Because k-means is much more robust. So it's good to give us the initial MI directly for our algorithms. And from from this original MI, we can just make the partitions based on k-means again. So we just have the initial MI, but we also have the assignments of data to each of these MI. And then we can evaluate the covariance matrix from these assignments based on that mean vector. So we get the initial SI that way. And then the prior can be computed directly from the BIT. This is kind of straightforward. So with k-means using, we can evaluate everything required to start to apply EM with multivariate normal distributions. Some things also we can do with EM is like if we are using multivariate normal distribution, we can do like what we have done with parametric methods. We can try to simplify the covariance matrix. So especially when we are dealing with high dimensionality, it may be an issue. So we are, for example, sharing the covariance matrix between the groups. That's one thing that can be done. You know, we need to redevelop the equations, but otherwise that's kind of straightforward. We can even state the covariance matrix as diagonal, so it will simplify the model, possibly make it less flexible, but at the same time, it may be good way to deal with high dimensionality, because with too many dimensions, it may be a problem. Or we could even use a covariance matrix that is the identity matrix times standard deviation. So it's really summarizing everything as I would say a bar defined by the sigma here, which is basically equivalent to the standard deviation in 1D. Another thing we need to know is that k-means is a special case of EM. So basically, if we make some simplifications, some basic assumptions like the a priori probabilities are equal for all groups. So for all groups, the pi I is equal to 1 over k. We are not looking at the real numbers. We're just saying that it is equal for everything, all the groups. If we use a shared covariance matrix defined here with like standard deviation estimation S, we've got this kind of splitting with HIT, which is corresponding to that with that simplification. And if we go in the beyond saying that in fact, the association BIT, which are either 0 or 1, are a hard version of HIT. So it's kind of discretizing HIT, assigning a 1 to the BIT, where the HIT is maximum for that sample over all possible groups. Otherwise, it's equal to 0. So it's kind of a binarization of HIT with the BIT. So with this 3 simplifications, we can state that basically k-means is an EM applied on multivariate normal distribution, where we are making these 3 simplifications. So basically, k-means use circular probability densities, while EM use multivariate normal distribution with ellipses. So basically, any shape of covariance matrix that leads us to any kind of shape of the function, probability density function associated to that group.